Director and so I'm going to start. Marilyn James of Sinite Station is going to do the welcoming. Then Mel Weezer will do climate change in the Columbia Basin. And thank you for coming. And lots of information on the table over here that you can take with. But we'll start with the welcome and thank the Sinite Station for hosting us here. Thank you, Marilyn.
I'd just like to take a minute to put down some tobacco on behalf of welcoming people to this event in our Ashtabula. Also acknowledging the work of the people who have been concerned about this landscape, concerned about what's going on this landscape, concerned about the water. It is all of our efforts on behalf of these things. One of us cannot do it all. Each of us has got to pick up our responsibility in what it is that we can do. So I'm very happy that Mel's here to do a presentation on climate change in this region. I mean, I've noticed since I've been here and occupying the Vatican occupation camp, the land is different. Where there was wild ginger that requires a moist undergrowth, it's no longer where it grew in plenty. There are so many things on this landscape that have changed in the last 20 years, it really concerns me. The water and the water pathways have changed, and that concerns me. There are so many things coming our way, but every way that we take to educate ourselves, to be more aware of what it is that's going on in this landscape and how it is that we ourselves can help in whatever way, even if it's just attending these kinds of events, educating ourselves and making sure that we do our share to make sure that other people know. So I want to also say, after Mel's presentation, we have a 13-minute video footage from the Unistoten. I think it's really important that we link these efforts that people are doing to protect the landscape and to do work for water. And so we always like to share those words on behalf of the people and know that our sentiments are the same. Water is an issue in this country, and I can tell you this, that where there are reserves, they seem to be a target for the filth that the government has managed. The people of Grassy Narrows cannot drink from their streams. They cannot drink from their taps. They have to drink bottled water. Other places of this globe, and I watched this video on Mexico, Coca-Cola went in there, ruined their whole water. Now they cannot even use water in their ceremonies. They use Coca-Cola on their altars because that's the only drinkable thing. I never thought I'd live to see that day, that we'd have more good Coca-Cola than we have drinking water. So I welcome you here. I really appreciate Mel being here and sharing his knowledge, and also I feel remiss that if we didn't acknowledge Marilyn Dragoon and her efforts on behalf of water and all that she does, we would be really remiss. She has kept a lot of our consciousness aware, and she's kept the Lemon Creek fuel spill alive, literally, and we're still fighting that. So these kinds of fundraisers go to that. So acknowledging this good work, acknowledging all of you here on this day who've shared a prayer with us at the water and have come and shared food with us, and now we share a little bit of food for the brain. And on behalf of the Sinaiacs, we offer this tobacco to the north, and to the east, and to the south, and to the west, and to our sacred mountains, Wawarkan, and we say, Lim, 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 lim. Thank you so much, Mel.
Thank you. Thanks for coming today. I appreciate the opportunity to talk to you about climate change. I'm going to be talking about 40 minutes or so, and it's a general presentation about climate change in this part of the world. And it's very similar to what I've been doing with the Columbia Basin Trust now for about 12 years. The Columbia Basin Trust has a climate change program, and we've gone to all communities in the basin and given sort of a similar presentation that gives people sort of an overview of how climate has changed in the past, what they can expect in the future, and the focus is on the steps that can be taken now to anticipate the climate change that's coming and to take steps to minimize the impacts of those changes that are coming. I work with a small consulting company called CRC. My colleague is based in Caslow. I live in Nelson. And actually, we just did 3 workshops in central BC with First Nations people in the Adams Lake area, Lower Sinoquemin, and Williams Lake. And we started these presentations with asking people to relay their traditional knowledge, what people have seen, what the First Nations people have seen in their landscape over their lifetime. And that was a real eye-opener because those folks are so in tune with what's going on in the landscape. And those workshops are really fruitful because they were able to gain some of the scientific information and the correspondence between the traditional knowledge and the scientific information made for an understanding that I think was greater than the sum of the 2 parts. Okay, so my background is in geology. And for a while back in the 1980s, I was a petroleum geologist drilling oil wells, so I probably have the biggest carbon footprint in the room. I went back to university. I got interested in research, looking at past climate change, and on the time scale of tens of thousands of years, not millions of years. And I'm just going to give you sort of a quick rundown of some of the findings, because I think the geologic perspective is important, and I will allude to that a couple times, but understanding how much climate change has changed in the past and why climate has changed in the past is a key piece of the puzzle for figuring out where we are now and where we're going. So, if I can get my technology to work here. It's not turned on, I'll do it. There we go. Okay. So I became interested in looking at the records that are in the sediments of alpine lakes. And this is up in the East Kootenays, just on the BC side of Lake Louise. And we're looking at 2 very high elevation lakes, one just below timberline and one just above timberline. And when you get a core sample out of these lakes, it's like a time machine going back in time. And you can see how the landscape has changed in the vicinity of these lakes. And what we were trying to do is figure out where timberline was in the past. It's about there now, between these 2 lakes. So this involved getting some core samples out of the lake's sediments. And basically, it's a tube a plastic tube that gets shoved into the bottom of the lake. And I did it in the winter because I couldn't afford to get a boat up to these lakes. So we used the ice pack as a platform. It was less expensive to do it in the winter. So basically, this pipe gets lowered down to the bottom of the lake on a rope, and it's vertical, 40 meters down below my feet at the bottom of the lake. And this contraption slides down the rope. It's full of concrete, and you just lift it up and drop it, and you hammer it into the bottom of the lake, fill up the tube with mud, and then you get a core sample. Getting it out, we were able to use or put ice screws in the ice and then use a pulley system so we could get the mechanical advantage to get it out of the lake. In some cases, we flew in. Sometimes it was by helicopter, but often we just would hike into these remote places, which kept me in pretty good shape. The other thing I discovered after the first trip, spending -30 in a tent was no fun, and we learned that there's some traditional knowledge around keeping warm in the winter, and that snow caves are a lot better. So this thing was home for 4 of us for about a week. And winter camping is not all that bad if you have the right equipment. It's a key piece of staying happy in the snow cave. Yeah. Here's what one of the core samples look like. So you can see the white is on the outside is the tube, and it's been split open. And there's layers here. As you go down this core sample, you're going back in time. and it's continuous, so you have a continuous record preserved in the lake sediments. And in all of the lakes that I've cored in this part of the world, you get this white thing, which is a volcanic ash layer. And this is 6,800 years old, and it came from what is now Crater Lake in southern Oregon. And it's all over the place, but the beauty of it is we know how old it is, and that gives us a timeline. So we know we're pre-6,800 years above that, and we're, pre-below that, and post-6,800 years above that. And then going further down in these core samples, we would run into glacial sediments at the bottom, so we have the whole post-glacial record. And radiocarbon dates from this contact between the glacial sediments and the organic mud came back to about 10,100 radiocarbon years. So you've got the whole post-glacial history in these tubes. I'm going to spend just a second on this diagram. It's a bit complicated, but I'll explain it. Because this is sort of, in a nutshell, one of the most important findings that we came up with after quite a bit of research. On the right is the lake that this came from. It's called O'Haven Lake. And you can see that right there where that red line is, that's where the glacier was in 1911. And there's pictures from the adjacent valley of the glaciers being that extensive. So we know that the ice was very close to this margin just after the turn of the last century. And here's the core sample, starting off very recently at the top and going back through time. There's a volcanic ash layer that's 2,000 years old. Here's that one that's 6,800 years old. And then the bottom of that record is 10,100 years old. And what you're seeing here are the different tree species. Pine, spruce, and fir across the top here. And these green bars are the needles, conifer needles. And the light green is a needle fragment, and the dark green is an entire conifer needle, and each one of these tick marks is 10. So this lake right here that is currently above timberline, that had a glacier in it 100 years ago, very much in an alpine setting, you go back in time during this interval from about 2,000 to about 10,000 years ago. The sediments are highly organic. You've got glacial sediments below and above. And you've got hundreds of conifer needles in a core sample that's only about 8 centimeters across. The only way you can get hundreds of conifer needles in this lake is if you've got a forest growing around the lake. And the sediments indicate that glaciers were present before 10,000 years and after 2,300 years ago. And in between, there's very likely smaller or no glaciers in that interval. So what we were seeing at these high elevation sites is they were very sensitive to past climate change, and they really recorded it nicely. And what we're looking at is a record of conifer needles, but there's a climate signal in that. That's telling you that timberline responds to climate. The warmer it is, the higher timberline is. Glaciers respond to climate. The warmer it is, the more restricted the glaciers are. So we had a really good record of climate change at this one site. And this gives us some insight into how much climate has changed in the past and where we're going. Another one that we looked at is going back in these core samples. And what I'm showing you here is a record from the Greenland ice core. This is the last ice age. This wobble here is called the Younger Dryas. It got warm, it got cold, and it warmed up. And here's the interglacial period that we're living in. So there was this oscillation called the Younger Dryas. And we were looking to see if we could see that oscillation in the local sediments. During this Younger Dryas period, in northwestern Europe, it was a major cold event. This, in white, is the extent of glaciers in Scotland during the Younger Dryas. So it was almost back to full glacial conditions for about 1,000 years. The line of reasoning about what happened there is that if you look at the ice sheet that was over eastern Canada at that time, about that time, was blocking the drainage across the continent, and there was a huge lake here that was draining down towards the Mississippi. About 11,000 years ago, just at the start of the Younger Dryas, the ice receded enough that it started to flow out to St. Lawrence, and you started to dump a whole bunch of fresh water into the North Atlantic. At the same time that the Laurentide ice sheet, this big ice sheet over eastern Canada, was starting to break up and flow into the North Atlantic, and probably the same from Greenland. So you're dumping a whole bunch of fresh water into the North Atlantic Ocean. That influences the ocean circulation. And that is what caused this wobble in climate. So our goal was to see if we could see this wobble that you see very pronounced in northwestern Europe and in Greenland, if we could see it in western North America. We went to a couple of sites in Colorado. There's Denver, this is Sky Pond and Black Mountain Lake. And I was with a group of researchers from the Smithsonian Institute, and they had connections with the local law enforcement. So we got taken into this lake by the Mineral County Snow Rescue Team, Basin, it was lectured. And this is Sheriff Leggett driving the vehicle, and you could have taken him back 100 years and put him on a horse, it would have been about the same. And here we are at the site getting the core sample, and there's Sheriff Leggett and Deputy Bob, they're rolling cigarettes. And watch, I think they call this the fellers from Universal. In any case, what we found, and this is to make a long story very short, is we found that in this part of the world, that change, that was a dramatic change in northwestern Europe, was about 1 degree Celsius or 0.6 degrees Celsius. So not as big a climate change as in northwestern Europe. And the reason that that's important is when we look at the old climate models. Here is a climate model from 1996, and you can tell in those days they were really pretty crappy. You can see that, you know, the continents are really jagged because the grid cells were so huge in those days. But basically, this is a general circulation climate model that what they did is they simulated all this fresh water coming into the North Atlantic. And sure enough, you get a decrease in temperature of about 8 degrees Celsius in northwestern Europe. But over here, in our part of the world, it's more like 1 to 2 degrees Celsius. All of this is to say that the climate models that we're using to project future climate in this part of the world, those models are validated and evaluated by checking their performance against past climate change that people like myself and thousands of others have worked on over the years. So there's a good way of telling whether, you know, how reliable these models are by looking at the geologic record. Okay, what I'm going to do now is shift gears and quickly review the idea of a bell curve, because we'll be looking at a bell curve fit to the local climate data here. And when I was in school, everything was graded on the bell curve. So if you had 100 kids in the class, you might have 24 C's and 30 B's and 21 B pluses, and then 18 A's, 1 genius, and then my end of the bell curve. But basically, it's the same thing with climate. When you're looking at a local climate record, you have a few cold years, you have a few hot years, but most of the years are around the average for that location. That's sort of the distribution of climate for a given location. And in this case, we're looking at mean annual temperature. If we increase mean annual temperature, that variability doesn't go away. It slides over with the mean, and you end up with a new climate. It has less cold weather, but it has more hot weather, and it has more record hot weather. And that bright red zone is kind of off the tail of the historical climate. And this is often where you run into trouble, because most built and natural systems are used to this distribution of climate. Most things are pretty happy if climate is within this range. Once it starts to move beyond this range, you get these extreme events that occur every now and then that often can cause problems for built and natural systems. Here's what happens if you increase the variability, sometimes called global weirding instead of global warming. So basically, if you do that, you have fewer years around the average, but you have more extreme cold events and more extreme hot events. And under those circumstances, you would have more record cold and hot weather, but in equal proportions. So here's what happens when you do both. You increase the variability, you move the curve over, and you end up with a new climate that still has some of the cold weather that everybody remembers from the historical climate. But in this case, now it has much more hot weather and much more record hot weather. And again, when you get into this area is when you run into trouble. So that's hypothetical. Now we're looking at some real information from NASA, and we're looking at Northern Hemisphere land summer temperature. And we're looking at the base period, 1951 to 1980. During that interval, this is sort of the distribution of climate, with a few extremely cold years, about a third cold, about a third normal, about a third hot summers, and then a few extremely hot summers. And as we go through decade by decade, this is the 1983 to 1993, 1994 to 2004, and 2004 to 2015. You can see what has happened is that the bell curve has shifted over to the right, and we have a new climate that has much more of this hot and extremely hot weather. So I think the numbers are coming up. So in the base period, 1951 to 1980, was about 30% were cold, 30% normal, 30% hot. In the last decade, about 80% of the summers were hot, and about 15% were extremely hot. In other words, off the tail of the historical climate. That's Northern Hemisphere land summer temperature. And we're going to, a little bit later on, zoom in on the local climate, what that looks like. But before we do that, I want to just talk about the difference between trend and variability, because this is often something that trips people up. And when you're looking at complex systems, like the climate system, sometimes it's really hard to see what's going on if you're focused in too much on the details, and that's the case here. In order to figure out what's going on, you kind of have to take a step back to see what's happening. And if you do that, you see what we're looking at is a guy out walking his dog. And if you want to understand where the dog and the guy are going to be in the future, you can forget about the dog because he's all over the place following his nose and leaps and bounds. But we understand that in about 10 seconds, intuitively we understand that the guy is going to be about here, even though right now the dog's going the opposite direction, right? Because we understand intuitively that it's the guy who's setting the trend, the guy who's setting where the dog and the guy will be in the future beyond a few dog bounds. And in terms of climate, and in terms of this guy, we have every reason to believe that he's going to continue on in the same direction in the future. The analogy here is that the guy is the climate and the dog is the weather, or the guy is the trend and the dog is the variability around that trend. So that's a hypothetical situation with a guy walking his dog. Here's some real climate data in terms of mean annual temperature from the Columbia Basin. And I think you see some similarities. It's very noisy. There's a lot of variability. And I think it's in our DNA to focus on that variability. We like to talk about how hot it was last summer or how much snow the winter before. But we're focusing on these peaks. And we kind of miss that underlying trend. And what's been going on is there has been an underlying trend that's been sneaking up on us, and will continue to do so in the future. And we'll get into the details of that. But I really want to emphasize, a lot of people will be focusing on the variability rather than the trend. And in the case of climate change, it's the trend that's the important thing to be thinking about. So we were looking at variability through time. The other thing I want to just touch on quickly is spatial variability. This is the summer of 2003. And a map of the world of the summer of 2003. You can see our part of the world was in a red area, which is warmer than normal by about between 2 and 4 degrees Celsius. But globally, it was about 0.57 degrees Celsius. That summer was about 0.57 degrees Celsius than summers in this base period, 1951 to 1990. But that additional heat wasn't evenly distributed all over the place. The Earth's weather systems kind of bunch it up into hot areas, which we experienced, but then there were cold areas, like over here in the Pacific and in Japan that summer. So it's not evenly spread out over the climate when we do get additional warmth. And it turns out, summer of 2003, I was living in Switzerland, right there in the middle of that bullseye. That was the European heat wave. And here's a bell curve of Swiss summer temperatures, and you can see that 2003 was off the end of the bell curve. And there were all kinds of problems. There were tens of thousands of people who died directly as a result of this heat wave in Europe. In our part of the world, we were warmer than normal as well, and everybody remembers 2003 as a bad fire season, especially around Kelowna. Scoot ahead to June 2015. Again, we had a really, really warm June. It was 0.77 degrees Celsius in our part of the world, warmer than the base period. And that had consequences. And this is the temperature record for June from Castle. And you can see the mean is about 14.5 degrees for June in 1961 to 1980 base period. June 2015 was 20.3, so 5 degrees Celsius warmer than the mean. And again, off the tail of the bell curve. And July 4th, 2015, we were already into a bad fire season, very, very early in the season because we had such a warm June. And for me personally, I was living at about 6 miles on the North Shore, which is right about there. That was too close for comfort. Scoot ahead to August 2017. And again, August 2017 in our part of the world was warmer than normal. And we had a horrible fire season in BC. But if you were in the Toronto area, you would have thought, well, it's fairly cool this summer. Move forward to February 2018, we had a really cold February 2018. But February 2000, there were headlines. It didn't take long before. What global warming, how about global cooling? So the inference is that global warming somehow disappeared because it was cold in our part of the world. But February 2018 globally was 0.82 degrees Celsius warmer than February's in this base period. And then scoot ahead to this last month. This information just became available a couple of days ago. February 2019, it was cold here. We had a real winter. And you can see in our part of the world, it was between 4 and 8 degrees colder than normal in our part of the world, clearly. But again, we got some people, in this case Donald Trump, saying, what the hell is going on with global warming, please come back. As if global warming had disappeared because it was cold in our part of the world. But in fact, February 2019 was 0.94 degrees Celsius warmer than the Februarys in the base period. It's just that it wasn't evenly distributed over the planet. So variability over time is important. Variability over space is important to make sure that we're distinguishing between the average and the trend. Okay, so now I'm going to switch gears and talk about local climate history. And I put together a regional climate picture for the Southwest Columbia Basin based on 6 Environment Canada quality-controlled meteorological stations. Castle, Farquhar, if I'm saying that correctly. Yes, thanks, I can read it. Castlegar, Creston, Warfield, and Grand Forks. And these are there's many more climate records in this part of the world, but these ones are quality controlled. They've been double-checked by Environment Canada to make sure there's no problems with the data. And this gives us a fairly good means for putting together a regional climate history. And of course, Crescent Valley here is right sort of smack dab in the middle of that. So when you look at those six different climate records in terms of mean annual temperature, you get a remarkable correspondence between them. If it was a hot year in Grand Forks, it was a hot year in Castle. They're all pretty much doing the same thing. They're not identical, but they're awfully close. And this gives us, confidence in that these records are all recording the same signal. And when you average that together, what you get is mean annual temperature over the last 100 years, and the trend of increase in temperature in this part of the world has been 1.5 degrees Celsius per century over the last 100 years. And the globe, the entire planet has warmed by about 1 degree Celsius over that same time frame. So we're warming here in this part of the world about 50% faster than the globe is warming. When you look at the last 50 years, in all cases that I've looked at in BC and in Alberta, you get the same story. Over the last 50 years, the rate of warming has increased. The rate of warming over the last 50 years has been 2.8 degrees Celsius per century, and compared to 1.5 over the last 100 years. And they're not always the same numbers, they're the same proportion, but always the rate of warming has increased over the last 50 years compared to the last 100 years. So looking at mean winter temperature, it's been warming more, 2.1 degrees Celsius over the last 100 years, and 3.2 degrees Celsius over the last 50 years. So in general, winters are warming up faster than the annual average. And if we look at summer, the rate of warming over the last 100 years in the summer has been a little bit lower, 1.1 degrees Celsius per century. But if you look at the last 50 years, it's 3.2 degrees Celsius per century. So things are definitely warming up annually, and they're warming up seasonally. In terms of mean annual precipitation, there's been an increase over the last 100 years of about 226 millimeters per year over the last 100 years. So we're getting more rain annually than we did 100 years ago. That rate of increase is backed off a bit. It's 150 millimeters per year increase over the last 50 years. But still, increases in mean annual precipitation. Now the next diagram is what's called a horundogram. And this is seasonal precipitation over the last 50 years. But what I did is I put in the heavy lines here to draw your attention to the means for the different seasons. You can see that spring and fall have been experiencing increasing precipitation in those seasons in this part of the world. But precipitation in the winter has been going down by about 38 millimeters per century. And precipitation in the summer has been going down by about 69 millimeters per century. But I think especially in recent years, what's of interest, if you look at the last couple of years of summers in this part of the world, they're down there. There's 2017, 2018. Some of the least precipitation in the whole history of this part of the world. And that has had some ramifications in terms of wildfire. Looking at the provincial totals, we can see that prior to the last couple of years, the biggest years were 1922 and 1958. And then there's area burn. 2017 set the record, and then we beat the record again the following year, 2018, with the most area burned in BC. And unfortunately, all indications are this trend is likely to continue. We're likely to experience more years like this. Now, just to understand how hot and dry things are getting, I've come up with a diagram that basically plots precipitation on this axis and temperature on this axis. And this is based on those 6 climate stations in this part of the world. And when you do that, you get, in this quadrant, years that are cool and wet, high precipitation, low temperature. And in this quadrant, you get years that are hot and dry. And here's the 20th century. Those are all years in the 20th century. And you can see 1922 and 1958. Those were the 2 big fire years before the recent 2 years. And they're both in this hot and dry quadrant. Now, what drives area burn in terms of forest fires is complicated. It's much more than just climate, but climate is a factor. And clearly, when you have a cold, wet summer, it's hard to get big forest fires going. So fire tends to like it when it's hot and dry, even though there's many other factors involved. Now, if we look at just what's happened since 2000, here's the 2000s in red. And you can see that the 2000s are definitely on the hotter side of the spectrum, and many of them are in this hot, dry quadrant. And you look at 2018 and 2017 are also in that hot, dry quadrant. So definitely when you have hot and dry years, like we've been having, and the trend has been towards hotter and drier summers, you end up with the potential for more intense wildfires, a longer wildfire season, and more area burned. And this is something that we've been working with communities throughout the Columbia Basin to get people's minds focused on, okay, we've got to start taking action, taking steps now to protect our communities from the potential interface wildfire. That's what August 12, 2017 looked like. I think 90% or 95% of the province was either high or extreme fire hazard. And this satellite image from last summer showed the smoke in our part of the world. And I think everybody remembers how horrible that was. Okay, I want to talk a little bit about extremes. Here we're looking again at the 6 climate stations in this part of the world in terms of mean annual temperature. And if we take an arbitrary cutoff of 9 degrees Celsius, these 2 years would have been considered extreme years in the early part of the 20th century. But because we've got this variability superimposed upon an increasing trend, those extreme years become more frequent, more intense, and longer duration. Sometimes you get 2 in a row. So this is what we sort of expect with hot extremes, is that as climate continues to warm, we're going to experience more of these record warm summers, or record warm years. And if you look at winter, it's a slightly different scenario. You don't get the increase in the high extremes as much. And when we think about extremes, we're often thinking about hot temperatures. But what's really interesting about the winter, if we take an arbitrary cutoff of 4.5 degrees Celsius, you can see that we had, on average, winters that had mean annual temperature below 4.5 degrees Celsius about every 6 years. And we've had one since 1986. And it's often these really cold years, these cold extremes in the winter, that are limiting factors for things like mountain pine beetle. So sometimes the extremes are really important because they, unlike the mean, that's not what's controlling the forest pests. It's these cold extremes. And the cold extremes have been disappearing. Okay, rainfall. This is something that's happening, I think, almost on a monthly basis. We hear in the news that somewhere there's been unprecedented rainfall and there's extreme flooding. I think in the last week, there's Nebraska has been having problems, and Mozambique and Zimbabwe have been hit by a torrential downpours, a cyclone that went through. And it makes sense. It's hard to predict, but it makes perfect sense. As the atmosphere warms, the ability for the atmosphere to carry more moisture, more water vapor, increases. And when you have more water vapor in the atmosphere, when you have fronts collide and it rains, there's more moisture that can come out of the atmosphere in the form of rain or snow. And this is the record from Caslow, looking at the June 19th event, 2013. This is 100 years of daily rain from Caslow, and you can see, those are the extremes. We're just barely sticking up. I think one exceeded 60 millimeters in a day. In fact, the average June precipitation for Caslow in the 20th century was 65 millimeters for the whole month. June 19th to 21st, during this one storm cycle, received almost double the monthly rainfall in 3 days. And this had consequences, with very high rainfall events. And in Nelson, you probably remember seeing the headlines in the Nelson, I think it was probably the Nelson Daily News then, of Ward Street turned into a river almost. That was an extreme rainfall event, but it only lasted 8 minutes. It was raining at 135 millimeters an hour for 8 minutes. and that overwhelmed the stormwater system. You can see the effects of climate change very obviously in glaciers all over British Columbia. This is the Kokanee Glacier, where it is in 2012, okay, 2010, and there's where it was in about 1870. It's receded dramatically, and you go across British Columbia. This is near McBride, in the northern Caribou Mountains. There's the glaciers currently, and there's where they were 100 years ago. And pop over to the Coast Range. There's the current glacial extent. I don't even need to, you can see where the ice was 100 years ago, the fresh moraine that's out there. That's how much ice recession there's been in the last 100 years. And this is pretty much happening globally. Glaciers are receding all over the place. So that's an indicator that we have ways of documenting by mapping, but we also have photographs. This is a picture of the Robson Glacier in 1911. That's where it was. That's where it is today. The recession of 2.2 kilometers roughly. So definitely, even without thermometers, we would suspect something is up with the climate because of the global recession of glaciers. And that has hydrological impacts. Some of the work that we've been doing for the city of Edmonton, they're very concerned about the extent of glaciers. Base flow that comes in the North Saskatchewan River, when all the snow is melted and you've had no rain for 6 weeks, a lot of what's in the river is coming from the glaciers, and there's concern that when the glaciers dry up, that summer base flow for the city of Edmonton may be a problem. And I did this about 4 years ago. This is data up to about 2014 from Redfish Creek, which shows what's been going on there. Spring flow in Redfish Creek has been going up by 68% since 1967 to 2014. And late season flow in the creek has been going down in September, which reflects hotter, drier summers and more precipitation in the spring, which we've been observing as well. So what we've been seeing in climate does have cascading effects into local hydrology. Okay, I'm going to switch gears now and talk about the future. And anytime we're talking about the future in terms of climate, we largely have to rely on climate models. And climate models are not perfect. And no one says there are. There's uncertainty with them. But probably the biggest uncertainty is not so much with the models, but which emissions pathway we follow. And what we're looking at here is, this is not temperature or any climate metric. What we've got here is billions of tons of carbon that we're emitting into the atmosphere, carbon dioxide. And you can see it's been increasing up to about 2017. I'm sure you've all heard of the Paris Agreement that Canada signed on to. And the idea, the goal, is to keep global temperatures to 2 degrees Celsius above pre-industrial or lower. That requires pretty drastic emissions reductions starting now, and actually negative emissions, so pulling carbon dioxide out of the atmosphere by mid-century. So those are the Paris Agreement goals. Here's a less aggressive mitigation strategy that maybe gets us to 2.5 degrees Celsius above pre-industrial. Here's what countries have pledged for the Paris Agreement. If you add up all the emissions reduction strategies that countries have said they would do for the Paris Agreement, you get to about 3 degrees Celsius. Notice that there's a big gap, a 1 degree Celsius gap between the Paris commitments and the Paris goals. And I don't know about all countries, but I'm pretty sure that Canada is not going to meet its Paris pledges. We're not going to get that target. So unfortunately, when we're dealing with trying to anticipate what's coming, we have to think about the worst case scenario, which is the business as usual scenario, which gets us to 4 degrees Celsius above pre-industrial. So the model projections that I'm going to show you for this area are going to be based on 2 different scenarios. One scenario, if we get pretty serious pretty fast about reducing emissions, and then the business as usual scenario. And I know that one of the leading consulting companies that's working with large cities like Metro Van, they just did a Metro Van report. They basically said the only scenario we're going to consider for now, for the city of Vancouver, is the worst case scenario because we see no indication of starting to bend the curve in these months. But I'm going to be more optimistic and say, if we really get it together, we're going to follow that scenario. When we're talking about those scenarios, we're talking about 2 degrees Celsius, 4 degrees Celsius. It doesn't seem like a lot. And this is where Earth history can really be useful for putting that in perspective. We're looking at the last glacial maximum. That was what the world looked like, looking down on the North Pole about 20,000 years ago. There was a continuous ice sheet from the southern Urals to Wisconsin, Midwest. This was the last ice age, 20,000, 18,000 years ago. Here's what the world looks like today, 2012, with the ice gone, and we're living in this current interglacial period. And the difference in global temperature between these two states, between the ice age and the interglacial period, is in the ballpark of 4 to 5 degrees Celsius globally. The worst case scenario that we're looking at by the end of this century is 4 degrees Celsius. So this is the planetary response to a change of 4 to 5 degrees Celsius. And in the worst case scenario, we're potentially going 4 degrees Celsius warmer than we are now into basically extreme waters. So although 4 degrees, 2 degrees doesn't seem like a lot, when you compare it to the difference it makes to the Earth in terms of glacial and interglacial cycles, it's pretty big. Okay, back to models. Models have gotten, I think, a really bad rap in the press. And this was just over a year and a half ago. Joe Oliver had basically said in the Financial Post, although you will not see this much in the media, climate model projections have turned out to be exaggerated, if not spectacularly wrong. And that's just not the case. But the problem is, a lot of people read this, a lot of people respect his opinion. So, to address that, I've just put together a few slides. On the right, we're looking at observed seasonal change in temperature. And on the left, we're looking at the Canadian ESM2 model. And you can see that during the winters, it cools more over the continents and less over the oceans, and same in the southern hemisphere. So this pattern of seasonal warming and cooling, more warming and cooling over the continental areas than over the oceans, the models get that right. In terms of circulation patterns, on the right, we're looking at a composite of satellite imagery, and you can see the counterclockwise storms in the northern hemisphere, the clockwise storms in the southern hemisphere, the intertropical convergence zone where you have these convective storms along the equator. And on the left is a model simulation. And it gets those patterns right. The counterclockwise storms in the northern hemisphere, clockwise storms in the southern hemisphere, and this drift of convective storms in the equator. And these patterns of climate, of atmospheric circulation are not prescribed, they're not coded into the models. These patterns emerge because the models are getting the physics of atmospheric circulation right. So the models aren't perfect, but they get a lot right. And as an exercise, what I did is, anyone can do this, I downloaded all the model data, and this is, starting in 1920, so the models go back in time as well as forward. There's the range of models, and yes, there's uncertainty. It's sort of a wide zone of different model possibilities. But here's the observed global temperature change over the same interval. And it's not perfect, but it's not spectacularly wrong. So the models are definitely doing a pretty good job of getting it right, and that shows up, I did that myself, but also showing up in major reports. This is from the US Global Change Research Program. And involved in that are, I think, 13 different U.S. agencies, including NASA, the National Science Foundation, the Department of Defense, Department of Commerce. And so this is basically what the scientists in the U.S. scientific community working for the government are showing, and what you've got are the models in orange and the observed in black. And again, there's not that much discrepancy. So we do have some pretty good confidence with the models. And lastly, I just want to talk about this guy for a second. He just died in the last month, I think within the last 3 weeks. His name is Wally Broker. And he was one of the early climate scientists who was concerned about climate change and said famously, the climate system is an angry beast and we're poking with sticks. He was also probably one of the most devious practical jokers in the scientific community, and was famous for that. He was a real character. He published a paper in 1975, so this is 45 years ago. And in this paper he said that the present cooling trend, because in 1975 the climate had been cooling off a bit, he said the present cooling trend will, within a decade or so, give way to a pronounced warming induced by carbon dioxide. In the early in the next century, which is now, we will have driven the mean planetary temperature beyond limits experienced over the last 1,000 years. And it turns out he was right. Going back to that US Global Change report, here's the last temperature, or the temperature change globally over the last couple of thousand years. You can see that's where we are today up here. That's the warmest it has been in the last 1,000 years. So Wally Broker got it right at a time 45 years ago when the modeling community was just really getting going. So again, we have reason to believe that the scientific community and people working with models, they won't give us a crystal clear picture and a crystal ball, but they'll give us a pretty good idea of where we're headed. So I'm going to switch gears and talk about local climate projections. And I'm going to be referring to this organization, the Pacific Climate Impacts Consortium. They're affiliated with the Canadian Modeling Group at the University of Victoria. And they have produced a suite of downscale models for across the country, across Canada. And the spatial resolution of these projections are now down to 10 kilometers on the side. So this is very specific to this part of the world. And what we're looking at in purple is one way of getting at how climate has changed here in the past. It's a gridded product. And what we're seeing in yellow, the heavy yellow line is the ensemble median. It's 12 different climate models. And the faint yellow lines are the different individual modelings. And with this major emissions reduction scenario, I said that there was one where we get serious about reducing emissions, and then there was the business as usual. With the major emissions reductions, we're looking at an increase of about 2.6 degrees Celsius in this part of the world above the 1961 to 1990 base period by the 2050s. For the business as usual scenario, we're looking at 3.3 degrees Celsius warming in terms of mean annual temperature. When we're looking at mean annual precipitation, it's not a big change, and there's a lot more variability. But the models are suggesting that with the business as usual and the strong mitigation scenario, we can expect annually something like 2 to 4% more annual precipitation. So not a big change in terms of precipitation. When you break this down seasonally, though, you can see that the models are suggesting we're looking at 5 to 6% more winter precipitation, and winter temperature going up between 2.7 and 3.1 degrees. And what this may end up doing in our part of the world, because we have topography here, is that this increase in precipitation in the winter, more of it at the valley bottoms is likely to fall as rain rather than snow. So we could have reduced snowpacks in the valley bottoms, but at the highest elevations, at 2,000 meters and above, there might be an increase of 5 to 6% in the snowpack at high elevation, which could potentially set up some difficult situations in terms of spring runoff, with valley bottoms being snow-free and more, 150% snowpack at high elevation. And I recall from last spring, there was concern about that. In terms of summers, summer temperatures are expected to go up between 2.5 and 3.5 degrees Celsius by the 2050s. Again, this is relative to 1961 to 1990. And summer precipitation is projected to go down by 7 to 13%. So again, in my view, for communities in this part of the world, a big red flag. We need to be thinking about hotter, drier summers and what that means in terms of wildfire and interface wall. We can look at some very specific aspects of climate now. In this case, we're looking at the number of days per year above the threshold. We can choose any threshold. And we've chosen 25 degrees. If you're above 25 degrees Celsius, it feels like a summer day. So we're anticipating that the number of days per year above 25 degrees Celsius will increase by 29 days with the strong mitigation scenario, and by 34 days with the business as usual scenario. So likely, yes, hotter, drier summers and more days where the maximum temperature is above 25 degrees, significant. And in terms of maximum precipitation, although the average precipitation annually is not expected to go up much, 2 to 4%, the maximum one-day precipitation is expected to go up 10 to 16%. So what this is reflecting is that it's very likely that there may be less rain in the summer, but when it rains, it really pours. So those maximum rainfall events are anticipated to become more extreme. And this has ramifications for especially stormwater systems. And I think I referred to this picture earlier. This is Ward Street in Nelson looking like a river. And if you were in Nelson this summer, you'll notice down off of Front Street, between Front Street and the Prestige, the road was all torn up. And the reason that they tore up the road is they were putting in bigger pipes to accommodate the anticipated increase in flow, to avoid that scenario. Okay, getting close to wrapping up here, what I want to do now is get a handle on the magnitude of the change that we're anticipating by comparing that to the local climate history of the 20th century. And this is what we're looking at here. Here's a histogram of mean annual temperature in the southwest Columbia Basin based on those 6 meteorological stations. And you can fit a bell curve to this data. And it's not a perfect fit, but this does pass the statistical test for being a good fit for the data. So that's the bell curve of climate in the southwest Columbia Basin. Coolest years were 5.5 degrees Celsius, hottest years were 9.5 degrees Celsius. And the average was around, I think there it is, 7.7 degrees Celsius. Now the model projections are always relative to that 1961 to 1990 period, which is here. And we're looking at an increase of 2.6 degrees Celsius, which is this much. And again, 2.6 doesn't seem like a lot. You go out your front door and it's 25 or 27.6 degrees Celsius, and your skin hits the air, you'll hardly notice the difference. But in terms of mean annual temperature, what this means is here's where your average year is in the 2050s. The take-home message here is that your average year in the 2050s is as warm or warmer than any year experienced in the 20th century in terms of mean annual temperature. And this is what the model projections are suggesting for the 2050s, about 30 years from now. And again, this is relative, the projections are relative to the 1961 to 1990 base period. But again, this is a significant change. And again, most built and natural systems are pretty happy under the historic distribution of climate. Now, these are based on climate model projections. Some people like Joe Oliver don't think climate model projections are very good. So there's another way of assessing this. Does this make sense? If we look at the rate of change of climate in this part of the world, again, based on those 6 stations over the last 50 years, it's been increasing at 2.8 degrees Celsius per century. The model projections are suggesting we'll hit 10.4 degrees Celsius by about 2055. If we simply extrapolate the rate of warming that's been occurring over the last 50 years into the future, we get there not 2055, but 2071, which is in the ballpark in terms of modeling. And this is important for 2 reasons. One is that often when we think of climate change, we think of something that's going to happen in the future. But the rate of change that has already been experienced in this part of the world over the last 50 years gets us to the situation where your average year is warmer than anything experienced in the 20th century by about 2071, mid-century. The other thing is that it suggests that the model projections are not outrageous. They're not unreasonable. In fact, they're fairly close to being what the rate of change that we've already experienced. So there's 2 lines of reasoning that suggest that the model projections are something that give us a general guide in terms of where the climate is going over the next 50 and 100 years, and provides a basis for us to anticipate the changes that are coming. So this is a map of the Columbia Basin, and it's going to show climate change over the last 50 years and then 50 years into the future, going from 1950 to 2050. And the temperature is color-coded here, and the blue are the colder temperatures, and especially when you get 0 and below, those are the areas that support the existence of glaciers. And you can see in the valley bottoms, we're looking at temperatures around 7 to 8 degrees Celsius. And as this moves forward, you'll see these blue areas get smaller, and you'll see into the valley bottoms some of these orange temperatures creeping in, which are getting closer to the mean annual temperature of Vancouver as this plays forward. So as mean annual temperature goes up, we can anticipate that we'll be getting hotter, drier summers, warmer, wetter winters, and it's very likely that we need to be worried about more extreme precipitation. So that's what the world looks like in this part of the world, mid-2050s, and you can compare that to the historic by looking at it, and the change that we're looking at is from 1.5 degrees Celsius to about 4.9 degrees Celsius. So pretty substantial change, and significant for many aspects of community operations and infrastructure that we need to be preparing for. Because this was the focus, or this part of the focus was on World Water Day and hydrology, I threw in one additional slide that looks at changes, hydrological changes. And I'm not a hydrologist, so I didn't want to go into much detail here. But this is the projected change in flow of the Columbia River at the Mica Dam. And And basically, it's the change in flow that it's looking at. So 0 is no change. And these are the months of the year. So by the 2050s, what it's suggesting is that April, May, June, the flow will likely be higher. And in July, August, and September, the flow will likely be lower. And again, this is something that needs to be looked at in terms of water availability and also in terms of hydroelectric generation. This is something that BC Hydro is very concerned about. This, not only the total amount of flow, but the change in flow. More flow in the spring due to the fact that we're getting higher spring precipitation, earlier snowpack melting, warmer temperatures, and lower flow in the summer months because we have hotter, drier summers, and the glaciers are smaller and providing less base flow into the river systems. So that wraps it up, and I'm happy to take any questions if you have some.
Sure.
And what we're going to see now is perfect timing because it's the First Nations people who have always led and are the leaders in terms of understanding and knowing what corruption with government and the land and these pipelines, etc. So thank you, Mel, very much
Thanks, Mel.
for